Hello. First of all, I would like to thank the organizers for inviting me to give a talk in this meeting. My name is Stefan Forste. I'm a physicist working at the University of Bonn. And what I want to do in this lecture is not so much to present my own research, but to talk about the subject of my research, how it embeds into the wider context. So the subject of my research is string theory. And here I will talk about unification in physics and how string theory is related to unification in physics, but I will not present any results of my own research. Okay, so let me start with the outline of my talk. So first I will discuss several instances where unification appears in physics and where it is actually quite useful also. The first example will be the unification of electricity with magnetism, leading to electromagnetism. Then I will talk about kind of unification of electromagnetism with mechanics that leads to special relativity, which then tells you that space and time actually have to be viewed as components of a unified space-time. Then if you go further and you unify the picture of special relativity with Newton's gravity, that takes you to general relativity. Or alternatively, you can unify the picture of special relativity with quantum mechanics, that takes you to quantum field theory and also particle physics. And then what I want to discuss after that is combining the two outcomes here, general relativity and quantum field theory, and unifying that would lead to quantum gravity, which is actually not so easy. And then string theory enters the picture. I will discuss string theory as a theory of unification, but I will also address some questions of quantum gravity where string theory might provide answers. Okay, so let's start with the simplest example, or the best known example of unification, and that is unification of electricity with magnetism. So if you first look at the phenomena of electricity and magnetism, they look quite different. So electricity you might associate to a lightning and a thunderstorm, whereas magnetism you might associate to a compass, where you have a permanent magnet as a needle, which shows you the magnetic field on Earth. But then actually when you do experiments, you pretty soon realize that the two phenomena are related. So the first experiments like that were performed by Ørsted and refined by Ampere later. And there you look at electric current through a wire, and then you realize that there will be a magnetic field around the wire, which can be detected with a compass. But also a magnetic field can induce an electric current, so the other way around. That was discussed by Faraday or found by Faraday. And here I have drawn an experiment where you can check this. So for here you have a first circuit with some alternating current running through a coil, and that gives some alternating magnetic field according to this picture. So here you have an alternating magnetic field, but then this alternating magnetic field induces an electric current in the second circuit, which can be detected with a lamp. Okay, and when you do all this, you get Maxwell's equations. So these I've written down here, so you can combine all these phenomena and write up a set of consistent equations. That was done by Maxwell, and these are the equations of electromagnetism. So E is the electric field, rho is the charge density, epsilon 0 is some constant depending on the units you are using, B is the magnetic field, and mu naught is another constant, and J is the electric current density. So these combines electric and magnetic fields into a set of equations, and that's a unified theory of electricity and magnetism. And one of the solutions, which is maybe particularly interesting, is electromagnetic waves, which are also known as light. And what you find out when you find these solutions is an interesting behavior of this light, namely its speed, the speed of light, which is just given by these constants, epsilon 0 and mu 0. The speed of light is always the same, no matter whether your source is moving or not, it's always the same. And if you plug in the actual numbers, you get for the speed of light 300,000 kilometers per second. So that's a very high speed of light. So now let's imagine you are inside a train and you walk in the train. And then there's some person on the station who measures your speed. And what the person on the station will find is that your speed is the speed of the train plus the velocity you are walking within the train. But now if the person on the station measures the speed of light inside the train, there will be no adding of the train's velocity. So as long as the train is very slow compared to the speed of light, the difference is actually very small. But if the train is moving very fast, then the phenomenon is quite observable, that the speed of light on the station is not the speed of light inside the train plus the speed of the train, but the same as the speed of light inside the train. So that's something which is not very intuitive because the train never goes that fast, but still it has to be taken into account, and you have to modify mechanics to include that effect, and that leads to special relativity. Sorry. And here I've written down two equations of special relativity, namely time dilation and length contraction. So what I want to emphasize here is now that time also becomes observer dependent. So the observer measures, the observer is now moving at the speed v, c is the speed of light, and the observer measures different time than the observer at rest. So that phenomenon is called time dilation. Or another way to see that, if something happens at the same time for the observer at rest, but maybe in different space positions, it happens also at different times now for the observer who is moving. So that's something new. When you combine Newton's mechanics with electrodynamics, you get special relativity. And then there's also the phenomenon of length contraction. So what you see here, time now also is observer dependent. Like space before, if you are moving, the coordinates of some object will behave differently than if you are at rest. Now that applies also to time, and in that sense time and space are combined or unified into the concept of space-time now. Okay, now let's discuss the next step of unification, which I want to focus on now, and that is unifying special relativity with Newton's gravity. So that is non-trivial, because in Newton's gravity, if you place a mass somewhere in the universe, then immediately it will attract any other mass anywhere in the universe. That's not compatible with special relativity, because the knowledge of that the mass has been placed somewhere takes time to travel to another place in the universe, because the speed of light is finite. So you have to do something to combine these two, and actually that has been done by Einstein, and it took him 10 years to find out how to do this. And what he came up in the end with is the theory of general relativity. And the new picture there is that now gravitational interactions are encoded into space-time curvature, meaning that there are some masses which curve space-time, and then other masses move on trajectories of shortest distance on these curved space-times, and that somehow tells you how general relativity, how mass interactions work. So let me illustrate it at the picture. The yellow blob here is the sun, and the blue smaller one is the Earth. And I've drawn here space only two-dimensional. So the Earth is moving in a plane around the sun, so it's enough to focus on 2 dimensions, 2 spatial dimensions, and these are drawn here as the horizontal line along the screen and the horizontal line perpendicular to the screen. So these are the 2 space dimensions, but the vertical line is not a space dimension. The vertical line is the size of curvature, say. So up here the curvature is small, down here the curvature is big. And and the black line is the size of curvature as a function of the distance from the sun. So here, if you are close to the sun, the curvature is big, and if you are further away from the sun, the curvature is smaller. So that somehow mimics the curved space-time, and now Earth is moving on a so-called geodesic, on a trajectory with shortest distance in this curved space-time, and that gives the actual orbit of the Earth around the sun. Okay, now let me discuss another. So let's forget for a moment about gravity. Let's look at another place where unification with special relativity does something interesting, namely quantum mechanics. So in quantum mechanics, you usually discuss fixed number of particles, often just one. And now if you want to combine this with special relativity, that's not a good thing because of the uncertainty principle. So in the uncertainty principle tells you if in quantum mechanics you are resolving very short distances, you pay with very high uncertainty in the momentum. And now we have seen we have to unify space with time, saying that if you now have you are resolving very short time differences, you have to allow for a very high uncertainty in energy, which is like the momentum and time direction. So you have to allow for a very high uncertainty in energy, but now energy can be converted into particle creation. So if the energy is very uncertain, you have to allow for the creation and also for the annihilation of particles. And that's what quantum field theory does. And quantum field theory combined with special relativity also gives you a particle physics description. And that comes about as follows. The particles now correspond to fields, meaning quantities depending on space and time. So that's fields, in particular representations of the Lorentz group. So that's a bit of a technical term. It means that if you know the fields for an observer at rest, there's a prescription to compute it for a rotating observer or for observer at constant speed. And knowing this prescription is often indicated as knowing the spin of the field. So here I've written down a spin 1 field, and that is associated to spin 1 particles, which are photons and gluons, for example. Here I've written down a spin 1/2 field that is associated to spin 1/2 particles like electrons or quarks. And here I've written down a spin 0 field, and this corresponds to a spin 0 particle, which is, for example, the Higgs particle. So that's a way to do particle physics, and then for particle physics you have to write down a very specific quantum field theory describing all the particles you have observed so far. And this has been done and also led to a concept of a further unification, namely unifying the electromagnetic interaction with the so-called weak interaction into the electroweak interaction. So the weak interaction is maybe something which escapes a bit the daily experience. It's some interaction which is important, for example, in nuclear fission. And but then you can unify these two, and first that gives some elegant description, some aesthetical view, and leads also to the standard model of particle physics. But it also led that time to the prediction of new particles which hadn't been observed so far, and these particles were actually discovered after they have been predicted. So the most exciting example might be the Higgs particle, where it took 50 years between prediction and discovery of the Higgs particle. Okay, so that's a standard model of particle physics, very successful, that contains few steps of unification, the last one being the one of electromagnetic and weak interactions. Now, hypothetically, you can go one step further, namely take these electroweak interactions and unify them with the remaining strong interactions. So the strong interactions are the interactions which keep the nucleus together, or the interactions which keep the quarks inside the proton together. And these, together with the electroweak, lead to so-called grand unified theories. And these theories have been constructed, but they are still speculative. So, for example, they predict proton decay, But experiments so far only gave lower limits on the lifetime of the proton. So proton decay hasn't been observed yet. So first you have to observe proton decay perhaps to verify that these theories are actually realized in nature. Okay. But let's also discuss one further aspect of quantum field theory. It also gives some nice view on how interactions work. And for that, I have drawn here a so-called Feynman diagram. So the Feynman diagram, when you first look at the theory, do computations, might be considered as an abbreviation for certain integrals to organize your calculations. But apart from that, it also gives you some intuitive picture on how interactions work in nature. So here I've drawn this Feynman diagram. There you should imagine that time runs vertically, maybe from down to up. So in this direction, time runs. The solid lines are electrons. So one electron comes in from the left, another electron comes in from the right. And then when the electrons are close enough, they start to interact. And the interaction is done by exchanging photons. So here there's one photon exchange. So the wavy line is a photon. This is exchanged between the electrons. And by exchanging the photons, the electrons repel each other and travel off in different directions in the future. So then it would be maybe very nice to have some picture like that for all the forces. So we have it so far for the strong and for the electroweak forces, because these are both described as quantum field theories, but it would be also nice to have it for the gravitational force, so that you have masses coming in, exchanging a graviton. Now they would be attracted to each other, and then they change direction and travel off. But when you try to do that, that's difficult, first of all, because of some technical reasons. So Einstein's theory of gravity is not renormalizable. That makes it different from the other theories. So you cannot just use the same methods. But then you think, oh, maybe this is just something aesthetical, and you don't worry about that. But then there are situations where actually it can be important to unify quantum theory with gravity. So that would be unifying quantum theory with gravity. So it's not important at collider experiments. At the LHC, you don't have to do that. Their corrections due to quantum gravity are certainly negligible, but there might be situations where it is important. So that is, for example, the Big Bang singularity or black holes. So the Big Bang singularity is something when you look at the evolution of the universe and you extrapolate what you see today backwards in time. So if you do that, at some point, the curvature of space-time becomes very high, and classically it even diverges. But before it diverges, there should be quantum gravity should be important and modify what you get. So for that, you need quantum gravity for the very early universe, and also for the physics of black holes, which I will discuss a little bit also later. So in black holes, you have some mass, and that contracts because of the gravitational force pulling the particles of inside the mass together. And if there is no force counterbalancing this gravitational pull, the mass will collapse further and further, and finally also end up in a space-time singularity, curvature singularity. But actually, before that happens, quantum gravity should be important. Okay, now we have seen that doing quantum gravity in conventional field theory is technically difficult, and that will be the first aspect of string theory I want to discuss. So before discussing these aspects of string theory, I've drawn two strings here. So a string is a one-dimensional extended object, like the string of a violin, for example. And here I've drawn an open string with two ends, and here I've drawn a closed string with no end. Okay. And now you want to look at the theory of strings and connect it to particle physics. And one way to see how it's done is easy. When you look at Einstein's formula, E is equal to mc squared, then you might associate the energy of the string with the mass of a particle, and that's actually also what happens. So if you have a string which vibrates only a little bit, it doesn't have much energy, that would be associated to a light particle with a low mass, or even massless. And if you have a string vibrating a lot, that's associated to a massive particle with a high mass. Okay, and then you can also associate spin to the string. There you have to actually look a bit more into the calculation. So let me not do that here, but give you the result where some of the vibration mode, or actually you can translate all the vibration modes of the string into masses and spins of particles. And here I give you only some of the resulting spectrum, namely only the lightest one, actually the massless spectrum of the string. So if you look at the closed string, then you find there's a spin 2 particle, which is massless. So I focus only on the massless particles now. You find a spin 2 particle which is massless. So that's a graviton. So actually, within your theory, you can describe the graviton. So you have a state corresponding to the graviton. So you have quantum gravity. Then also you can look at other possibilities. So for example, if you look at the open string, there can be a spin 1 massless particle in the vibration mode of an open string. And that would be your other interactions, like the photon for electromagnetic interactions or the gluon for strong interactions. Then to get your electrons and quarks, you have to add supersymmetry, then you also have spin 1/2 excitations of the string. So what you see, that string theory captures all known particle physics, including gravitation. So it unifies all known particle physics. Strong, electroweak, and gravity. So one question now is, what can we learn about this? So the caveat here about quantum gravity is that this has been done in flat Minkowski space. But I have argued before that quantum gravity is important for strong space-time curvature. And then actually it's quite difficult to do string theory in strongly curved space-time. So although string theory is a consistent theory of quantum gravity, it's still difficult to get answers in situations where quantum gravity actually matters. So let me describe one of such situations first before discussing how string theory deals with that situation. And that is about black hole physics. So first I've drawn a black hole here, very simplified. So I've focused only on 2 dimensions. So this is actually 3-dimensional with spherical symmetry. So this blue circle is actually a sphere in 3-dimensional space. And now when a star collapses, it collapses further and further. If there's nothing to counterbalance the gravitational pull, it collapses finally to a point. That leads to a singularity in space. And now in my 2-dimensional picture, this will correspond to the center of this black circle. And now this singularity in space has a strong gravitational force around it. And that gravitational force is even so strong that light cannot escape the field of gravity. That's why these objects are called black, because light cannot escape, they look black. And actually the place beyond which light cannot escape is called the horizon, and that is indicated by this black circle. So inside this region, light cannot escape the gravitational field of the collapsed star, and outside it can. And now there can be situations for big black holes that the space-time curvature at the location of this horizon is not very big. So there you can treat gravity classically, and you can do just quantum field theory for other forces in a slightly curved space-time. And this has been done by Hawking, and what the result of Hawking's discussion I discuss here in a more heuristic way to give you some picture, some intuition about it. So when you do quantum field theory in general, I talked already about the uncertainty principle. There's this uncertainty principle telling you that in very short time intervals, there can be a creation or annihilation of particles. So that I've drawn here as a bubble. So there's in a very short time interval, there can be a creation of particles, and they travel for antiparticle pairs. They travel for some time and re-annihilate each other. So this happens all the time in the vacuum, and this is okay. That doesn't cause problems. But now if you do this near the horizon, it can happen that one of the partners in this pair creation falls inside the black hole, and the other partner is radiated off to infinity. And now when you look at this process, you find, if you do the detailed calculations, you find that you get radiation which is thermal. So this means that there's a certain characteristic dependence of intensity. Intensity is depending in a certain way on the frequency of the emitted radiation. And there's a very characteristic profile, and there's a one-to-one correspondence from this profile to a temperature. So that way you get a temperature for this black hole, and this is called the Hawking temperature. And this temperature is inversely proportional to the mass of the black hole. So it goes like 1 over mass of the black hole. And now we have seen that quantum mechanically the black hole loses energy via radiation, and this can be achieved only by you losing mass. So mass is converted to energy. But now if the black hole becomes lighter, its temperature becomes higher, because temperature goes like 1 over mass. In other words, the black hole has a negative heat capacity. It radiates off radiation and becomes hotter. And that's a very unstable situation that leads to the black hole's evaporation. The black hole will evaporate at some point in the future and leave only this thermal radiation. And then the paradox is, if you have only this thermal radiation, you don't know very much about the black hole. So to explain the paradox, I have to describe other situations in physics. So any situations which is not black hole physics, so far in physics, is like that. If you have your system at a given point in time and space, and you know precisely what its state, you measure precisely every aspect of the system, you will be able to predict or tell what the system has been sometime in the past or sometime in the future. So the information is never lost. So you can extrapolate back in the past and you will exactly know what your system has been in the past. But here, when you have this evaporating black hole, you just get this thermal radiation, no matter what the black hole was made of. So all the information on the details of the collapsing star is lost in the process of an evaporating black hole. So that seems very puzzling, because it doesn't fit other experiences. So now let's see what string theory has to say about that, or get some clue what string theory has to say about that. And for that, the concept of D-branes is important. So D-branes are objects where an open string can end on. So D stands for Dirichlet, and branes comes from membranes. So these are extended objects, in this picture two-dimensional, but they can be also one-dimensional, three-dimensional, whatever. So these are objects, extended objects, where an open string can end on, meaning that the ends of the open string have Dirichlet boundary conditions in this direction, and Neumann, so-called Neumann boundary conditions. They can move freely in that directions. When you look at the theory, you can quantize these open strings or look at vibration modes of the open strings, and that gives you at most spin 1 particles. And that is just ordinary quantum field theory, and in such a theory, information will never be lost. But you can also look at a picture where the open string joins ends, becomes a closed string, and is emitted from the D-brane, or actually a closed string can be also absorbed by the D-brane. And in the closed string spectrum, there was a graviton. This means the D-brane interacts gravitationally, or in other words, it carries mass, and that leads to space-time curvature in general. And now there's a tricky limit where you can actually do a limit such that the two descriptions with the closed string or the open string are really complementary to each other. And this is the so-called Myracinal limit. And that leads to the so-called ADS-CFT duality. And without going much into the details, I'm telling you that this relates some theory with gravity, which is difficult to quantize, to some theory without gravity, which is easy to quantize. And there's actually a one-to-one correspondence with these two. And that is rather surprising. Even the dimension of these two theories differ. So this is a d+1 dimensional theory with gravity, and this is a d-dimensional theory without gravity. And now you can say that the process of an evaporating black hole must correspond to a certain process within a theory without gravity. That process might be very complicated, but it is some process in a theory where you know that information is never lost. So that leads to the conclusion that information is never lost in black hole evaporation either. And then there are interesting questions on how this happens in detail, but let's not get into that. And let's summarize. So what I've argued here is now that the concept of unification in physics has been very successful. It even led to predictions of particles. It gives a very efficient way of describing nature, and it has proven very useful. Now, string theory I've introduced as a theory unifying all particle physics, so all the particles become excitation modes of a string, and even the graviton now appears on the same footing. In that sense, string theory is also a theory of quantum gravity. But then when you actually want to apply string theory to situations where quantum gravity is important, it's still difficult to do that, but there has been progress. So, for example, discovering this ADS-CFT duality led to the prediction that the black hole information paradox is solved in the way that information is actually not lost. So after that, I would like to thank you for your attention. But before finally really closing the talk, I would like to advertise our graduate school here in Bonn. So this is called BCGS, in short, Bonn-Cologne Graduate School of Physics and Astronomy. And what is particular about this is that it focuses not only on PhD but also on master studies. So if you have a bachelor or you are getting the bachelor in the near future, you might check this out. And there are even some stipends covering your living expenses when you do the masters in Bonn. So please check this out if you are interested. Then now I thank you for your attention. Bye-bye.